All right. So longitudinal force transfer, really important for rate of force development so that you can have that go along. And you can see longitudinal force transfer again is when we've got this going through titin, going through the Z-line, so alpha-actinin within this structure. So all of these structures along the length of the fiber or along the length of the sarcomere. When we're talking about lateral force transmission, now what we're talking about is the transmission of force across fibers and between fibers and into the extracellular matrix here. So we've got the extracellular matrix, we've got the integrins here, and the integrins are going to link into the extracellular matrix. And they're going to be brought in around the Z-line as well, where you've got desmin. And then you've got this really important protein, dystrophin, that everybody's heard of because of muscular dystrophy. And what dystrophin does is dystrophin sits here at the outside of the muscle fiber, and then it connects up to this dystrophin-associated glycoprotein complex. All it is, you can call it the DGC, the dystrophin-associated glycoprotein complex. And what it does is it connects the inside, the dystrophin and the actin, to the outside, the collagen. And that's all done through this protein complex called the DGC. And so when you've got dystrophin, you're contracting the thick filaments here, you're cycling the thick filaments, your thin filaments are moving in, that's pulling on the actin, and that's then transmitted through dystrophin, out through the DGC, into the collagen matrix, and through the collagen matrix into the next adjacent fiber. So longitudinal force transmission is along the length of the fiber. Lateral force transmission is laterally and between fibers. So it's connecting two different fibers that are overlapping. And that's going to be really important for preventing shear. Shear is when the fibers slide. And you can see that if the fiber slides, it has integrins, it has DGCs, it has a bunch of stuff. And if you're sliding, what's going to happen is those things are going to act like little anchors, and you're just going to start pulling out holes. So you're going to make little holes in the membrane, and that's going to really affect how well your muscle works. So that's really something that you want to prevent. Okay, and this is where the paper that we're talking about this week or today comes in, because what we're going to talk about is this idea of what this group, Ramaswamy, out of John Faulkner's laboratory at the University of Michigan did. And basically what they did is they measured force using two different systems. One is to measure force using the tendon. So they put a force measurement on the tendon. And the other, because this group works very closely with plastic and reconstructive surgeons, they have very, very fine, very high level, very high quality surgeons who can sew. And what they sewed onto the outside of the outside muscle, so the epitenon in the fascia overlying the muscle, was they sewed this little thing they called a yoke. It's a little plastic device. And then they could run sutures from the yoke to the force transducer. And so what they would have is they would either have force measured at the tendon or force measured at the yoke. If the force measured at the tendon is longitudinal force and it's going to be a lot or all of the force, then when you measure force at the yoke, it shouldn't really do anything. And you shouldn't see any force. But what you see in this situation is that this is the force measured at the tendon on the x-axis. That's the longitudinal force. The lateral force measured at the yoke, now what you see is that force is going up almost exactly with the longitudinal force. So that means 100% of the force is coming out there. When you get up to higher forces, we're seeing that it's going down. And as much as I think that may represent physiology, it could also represent that even though these are incredible surgeons who are able to sew this microscopic level sewing so that you only get the epimysium, it's possible that their sewing wasn't perfect. And so that difference is maybe reflected here. But regardless, even if you take it that means that this is real and only 80% of the force is transmitted laterally, that's still really a high number. And so what they then did is they started to try and figure out what was going on with that. And the way that they did it is they took mice that lacked dystrophin. And so you can see these are wild type mice that have the normal dystrophin protein. The longitudinal force between the two of them is about equivalent. So you're not seeing a huge difference. You can see that 80% of the longitudinal or the force is transmitted laterally. Another thing you should see is that the rate of force development in the lateral force development is slower than the longitudinal force development. Again, that's telling us a little bit about what these structures are. Now what you can see is 80% of the force here is transmitted laterally. Now if we go to the MDX mice muscles that have no dystrophin in them, now what we see is we're losing a whole lot more of the force. So we're going from about 14 to 1500 down to about, so here we're only transmitting 50% of the force. So if you don't have dystrophin and you can't transmit force, you just don't transmit force as laterally as well as when you do have dystrophin. And so what that means now is that we're not connecting the fibers as well, because remember, this lateral transmission means that we're not connecting the fibers. So what does that mean as far as muscular dystrophy, as far as this disease? Well, what we have here is from Dennis Claflin and Sue Brooks. They took working videos of the bottom side of the foot where you've got this this muscle called the FDB, or this pedicle muscle. And what it is the bottom of the foot, so you can actually see the individual fibers under a microscope. So this is just 1 or 2 fibers thick, so you can actually see the different muscle fibers. And that's really important because this is the wild type muscle, this is normal muscle, and it's just contracting, and you can see it contracting, and the whole thing contracts, all of the fibers contract together. Now, if lateral transmission is lost with dystrophic muscle, and lateral transmission is important in preventing shear between the fibers, in the dystrophic muscle, we should be able to see more shear, and we should be able to see what happens as a result of that shear. So when we start this video, this is going to be 10 contractions now, and what I want you to look for is how different fibers are moving differently relative to each other. So you see where the red mark is there, is you have these fibers that are sliding now. And when that happens, you get little holes in the membrane. And when you get holes in the membrane, you get calcium influx from the outside of the fiber. And when you get calcium influx from outside the fiber, you get small areas where you contract the muscle a whole lot, and other areas where you don't contract the muscle at all, because the calcium is localized to a small area of where the damage was. And you can see that this, I only showed you, I think, 5 of the 10 contractions, but it's an isometric contraction here. And what you can see is that you've got all of this damage that's been done. You've got this huge amount of damage done. And so what this means is that muscular dystrophy is really this disease that is this disease of impaired lateral force transmission. And when you have impaired lateral force transmission, you get more muscle damage that has to be repaired and regenerated. And if you continuously are damaging and regenerating your muscles will eventually begin to deteriorate. So as far as lateral force transmission, so when we talk about the force transfer apparatus, we're talking about both longitudinal, along the length of the fiber, and that is necessary for rate of force development and to transfer force to the tendons really well. And then we need to laterally transmit so that the muscle all of the fibers get linked together. And lateral transmission, what it is doing is protecting those individual muscle fibers from injury. The way that I like to think of it is, if you're a sardine and you're by yourself in the middle of the ocean, the likelihood of you surviving as an individual is very, very low. So what do? You get together with thousands of your friends. And because you have thousands of sardines now, the likelihood of any one sardine being injured or killed goes down. And so when we link thousands of sardines together, each individual is protected from injury. Just like when we link thousands of muscle fibers together, we're protecting them from injury. And the weaker the link is, the more susceptible you are to injury or being eaten, depending on which part of the analogy we're in. All right, so as longitudinal force transfer is lost, the rate of force development slows, making people more prone to falls, making performance decrease. But it's really this idea, if you're walking along and you don't see something, you trip, and suddenly you're slow to get your foot out in front of you, you're going to fall. So all of these things actually could be important in what happens to our muscles as we age and as we do performance-based work as well.